Okay, let's take a look at a couple of example problems. We'll work through one example that has distinct real roots, and in the other example we'll look at a problem that has complex roots. So this is problem 2.2-1, in which you're given in operator notation a differential equation, d squared plus 5d plus 6 y of t is equal to d plus 1 x of t. This of course would correspond to the differential equation dy squared dt squared plus 5 dy dt plus 6y is equal to dx dt plus x. In part A of the problem, we're asked to find several different things. We'll introduce some terminology here. This portion of the differential equation is what we called the polynomial q of d, so the characteristic polynomial is just q, and we substitute the variable lambda into the characteristic polynomial. That just becomes, we're just replacing d with lambda, so we get lambda squared plus 5 lambda plus 6. This is the characteristic polynomial. The characteristic equation is what results when we just set the characteristic polynomial equal to 0. So it's lambda squared plus 5 lambda plus 6 is equal to 0. That's the characteristic equation. We can factor this quite simply in this case as lambda plus 2 times lambda plus 3 is equal to 0. You can multiply that back out and verify that it gives you the polynomial expression above. And then, so the characteristic roots are the solutions to the characteristic equation, the values of lambda for which the characteristic polynomial is equal to 0. Of course, we could use the quadratic equation to find the roots in this case, but since I factored it, we can see by inspection that the characteristic roots are lambda equal minus 2 and lambda equal minus 3. Just set lambda plus 2 equal to 0, and then lambda plus 3 equal to 0. And then the corresponding characteristic modes are the functions e to the lambda t. So we have two values of lambda here, so one mode is e to the minus 2t, the other mode is e to the minus 3t. In part B, we're given the initial conditions on y of 0 at 0 minus, that's equal to 2, and at y of, and at on the first derivative at 0 minus, and that's equal to minus 1. The general form for y0 of t is just the sum of our modes with arbitrary constants. So c1 e to the minus 2t plus c2 e to the minus 3t. So we'd have a different arbitrary constant for multiplying each of our modes. We'll apply this first initial condition. We just substitute 0 for t. We'll talk about the significance of the 0 minus notation a little later on. Right now it's not important to us. 0 minus at this point we can consider to be the same as t equals 0, so plugging in t equals 0, this equation becomes y of 0, evaluate e to the minus 2 times 0, that's just 1, so this becomes c1 plus c2. To apply the other initial condition, we need to find first the derivative of y0 of t. So take the derivative of this term, the minus 2 comes down, I get minus 2 c1 e to the minus 2t, and then I'll have minus 3 c2 e to the minus 3t. Again, evaluate this at 0, and we get y0 at 0, and then this reduces to minus 2 c1 minus 3 c2. Okay. Now I have to plug in my initial conditions. I know that c1 plus c2, that's y of 0, that's 2. So I have c1 plus c2 is equal to 2. And then the initial condition on the derivative, I get minus 2 c1 minus 3 c2 is equal to minus 1. Okay. Use whatever from this, whatever method you're comfortable with to solve this set of equations. I can multiply the first equation through by 2 and then add it to the second one. I'll immediately get minus c2. So here these terms would cancel. Here I'd have plus 2 c2 and a minus 3 c2. That leaves me with a minus c2. Then I'd have 4 plus a minus 1 is equal to 3. So this gives me c2 is equal to minus 3. Plug that back into this equation. I'll then have c1 is equal to 5. Plug those two values into the bottom equation just for a check. Minus 2 times c1, which is 5, gives me a minus 10. And then I'll have minus 3 times minus 3, that's plus 9. So minus 10 plus 9 is equal to minus 1, so it checks. So this is the solution to this pair of equations. Again, in that case, you can use back substitution. We can use matrix methods, whatever to come up with the solution. So this finally gives me now the complete zero state solution. I just plug the c1 and c2 constants back into this equation. So c1 was 5, and that's times my e to the minus 2t mode, and then c2 is 3, minus 3, and that's e to the minus 3t. And so this is the zero state solution for this differential equation that satisfies the initial conditions. Okay. Let's take a look at a second example. Problem 2.2-4, and the shorthand notation, the operator notation representing the differential equation is d squared plus 9. Y of t is equal to 3d plus 2 x of t. Of course, you can see by inspection what the corresponding differential equation would be, I hope. And then so our characteristic equation, and we set the right hand side, the side involving the input x, equal to 0, and for our characteristic equation then becomes lambda squared plus 9 is equal to 0. I can factor this into the form lambda minus j3 and then lambda plus j3. Okay. Set that equal to 0. and I get the characteristic roots of lambda equal to plus j3 and minus j3. Okay. These are the characteristic roots. In this case, they're complex. They don't have a real part though, so there won't be an e to the alpha t part. We'll just end up with the cosine part when we substitute into our expression. So this is the characteristic equation. This portion, the lambda squared plus 9, set that equal to equivalent. This is what we call the characteristic polynomial, and then these are the characteristic roots. So the corresponding modes would actually be e to the j3 and e to the minus j3. Okay. And we could write the solution in terms of the characteristic modes. Again, I prefer to use the shortcut method, or a simpler method where we actually write the zero input solution as a cosine of, in this case, 3t plus theta. I made a mistake on my modes. I left out the t on both of them. Okay, so again, it's important that we have, because there are two modes, we will have two unknown constants here, a and theta in this case, and we're given the initial conditions. y0 minus is equal to 0, and the first derivative at 0 minus is equal to 6. So again, I will need the first derivative. In this case, the derivative of cosine is, I have to pull out the 3, and it'd be minus sine. So this is the derivative. I substitute in y0 of 0, and I'm going to get a cosine, substitute t equals 0, and I get a cosine theta, and that's equal to 0. Cosine of theta is 1, so this implies whoops, it should be not a cosine of 0, but a cosine of theta is equal to 0. Of course, I can't plug in a equal to 0 because that would give me no solution. So I'm interested in the values of theta at which cosine of theta is equal to 0. That's going to be at theta equal pi over 2 and or minus pi over 2. And then other 2 pi shifted versions of theta, which actually would just give me the same form of the solution. And then I also need to plug in my initial condition here for the derivative. That's equal to 6. So I'd have minus 3a sine, again with t equal to 0, I get theta, and that's equal to 6 at theta equal to pi over 2, sine of theta is 1, and then a would be minus 2. At the other case, theta equal minus pi over 2, sine of theta is actually minus 1, and then in that case, a would be equal to 2. So let's take a look at both of these possible solutions. A equal minus 2 at pi over 2. So one form of the solution would be y0 of t is a to the minus A is minus 2 cosine of 3t, and then in this case this is the plus pi over 2, and then the other form was actually y0 of t is 2 cosine of 3t minus pi over 2. Okay. Actually, these are identical solutions. If I can invert the amplitude by shifting the phase by pi, and so if I do that and take the minus sign, shift this by pi, I'll get minus pi over 2, and then pull the negative sign out front. So they're actually the same solution. So so we typically prefer to write these sinusoids with positive amplitudes. So the solution in this case, the zero input solution that satisfies the initial conditions, then would be 2 cosine of 3t minus pi over 2, or if you prefer to express the phase angle in degrees, minus 90 degrees.